Hi, I'm Melissa, Keysight Technologies. If you're making power integrity measurements, chances are you need a very accurate and specific test setup in order to capture the results you're looking for. You need something with low noise in order to prevent getting false negative results, something with really low loading so that your signal isn't distorted by the probe, something with high bandwidth so you can catch high frequency switching loads. And you also want a way to remove the DC offset so you can zoom in tight in your signal without using a DC block, which can filter out supply drift and other information in your signal that you want to observe and capture in your results. A standard passive probe is not going to provide all these solutions for you. So real quick, let's take a look at a standard passive probe compared to a specialized power probe. Connected to my S-series, I have two probes. On channel 2, I've got my standard 10-to-1 passive probe, and on channel 1, I've got my specialty 1-to-1 power rail probe. So let's take a baseline noise measurement. First, I'm going to zoom in a little bit tighter on these signals. I'm going to go to 10 millivolts per division on each channel. And then I'm going to ground each probe tip so we get a good baseline noise measurement. So I'm just taking off the clip here and I'm going to ground the probe tip with the clip there. And then with my active probe, this is actually a SMA connector. So I'm going to use my handy dandy screwdriver to gently make this connection here, this ground connection. And to free up my hands, I'm going to just go ahead and stop the acquisition. And now we've captured that measurement, so let's take a voltage measurement on each of these. So on channel 2, so on the passive probe, we've got, it looks like 26.7 millivolts of baseline noise. And on my active probe, I've got 1.6 millivolts of baseline noise. So that's about 20 times less noise on this power rail probe here than on your standard passive probe. Now that we've looked at baseline noise, let's look at how immune to noise these probes are. So now if we hold both of these probes up to the screen, we should see if they pick up noise from our capacitive touch screen. And you can see this passive probe here, it's really picking up a lot of noise. But this power rail probe, there's just not much going on there. It's really not picking up any of the noise from the touch screen. Let's go ahead and take a closer look at this. Let's go ahead and expand our view. Let's separate these into grids. Center the waveforms, just so we can really get a good look at what's going on. And both of these probe tips are held up to the screen, and again, the passive probe is really picking up noise, whereas this active probe is just really not. It's not picking up any of that noise. So this is really useful in a power rail probe because you don't want to be picking up noise spikes like this, because then you could trigger and you'd get false negative results. But not only does it have the noise advantage, it's also got 2 gigahertz of bandwidth. It allows you to remove the DC component without using a DC block, which, as I mentioned, can filter out supply drift that you probably want to measure in your system. The specialty probe that I've been using today is the Keysight N7020A power rail probe. And when you pair this with the S-series oscilloscopes, the result is a really powerful solution. If you watched my video from several weeks ago, you'll recall that the signal integrity of the S-series oscilloscopes is amazing. So when you pair an ultra-low noise scope with an ultra-low noise probe, the result is incredibly accurate measurements. Click on the link in the description to learn more about the probe and how it can help with your power integrity measurements. And if you enjoyed the video, please like, share, and subscribe to the Keysight Oscilloscope YouTube channel. I'll be here every other week until the end of December to talk about features of the S-series oscilloscopes.